Hello there and welcome to module 7. So this is topic 2. We're going to get deeper into our finite state machine and fault model. So now before we get there, let us probably spend quick time on understanding the modeling about what the system is and what the system does part of it. So I'm going to now take you to the textbook. We're going to use the document camera. What you're seeing now is the expressive capabilities of selected behavioral models. And on one column, what you see here is the behavioral issue. So we are seeing the behavioral issue and you've got source of the issue. So when we are looking at sequence, selection, repetition, it becomes part of the programming part. The issues where we are looking at enabling something, disabling something, triggering something, activating, suspend, resume, pause. We definitely understand that such a system would be useful for having an enable, trigger, activate for say a media player. So a media player would typically have such kind of functions, and that is where the source comes in. We look at it from a systems modeling language perspective. This is where I think we would want to figure out how the system is built from the state's perspective. Again, the next piece would be from a task management area. We look at, are the tasks conflicting? Is there a priority? If one is happening, the other cannot happen. So one is happening, the other cannot happen would mean on an airstrip, you would typically find that when there is a landing happening on one airstrip, you would not want a takeoff happening from the same airstrip. Maybe from the same airfield, but not on the same airstrip. And last but not the least, we're also talking about events, synchronous events, multiple events, or context sensitive input events. An enter key pressed when the focus is on a particular line edit would mean something entirely different than an enter key when the focus is not on that line edit or somewhere else. So it could be context sensitive. Now you can see that we can model the system in many ways. What are the appropriate choices? One of the other pieces that one would always ask is, what are these appropriate choices for our executable model? So you would see that we have the same behavioral issue over here. So the leftmost column is the behavioral issue, and then you've got decision tables, finite state machines, Petri nets, state charts, EDPNs, which will allow us its expressive capability to be used or no. So you would see a lot is done by state charts. Petri nets do quite a lot. FSMs do certain things. Thus, this table, which is on page 226 of our T1, would allow you to learn which tools would be appropriate for what kind of modeling. And we are learning and touching all of them from a test perspective. Now you may be wondering, why do we really need to learn all these models? This look like software design. However, understanding of the system is part of even testing. And we will look at examples where we are going to make use of the models that we spoke about, the behavioral issues that we are trying to address, as well as the executable models. Now I think we got to put all of this together to help create high quality test cases and a testing environment for us. So finite state machines, that's what we're going to look at. So it's a method of expression of a design. That's what we looked at. Simple way to model the state-based behavior. And we looked at this, that system is in one state, state 1, and the system does move to state 2 when there is input and then it also provides an output. Or it moves from state 2 to state 1 when there is another input with the output provided for as it moves from state 2 to state 1. And then you'll find state charts and Petri nets, which are a different extension. Especially Petri nets can help express concurrency and timing. You need something specific to happen, and it is based on timers. One of the easiest examples and the simplest examples that comes to my mind is a windshield wiper of a car. It has a state function, so I'm in state of low, medium, and high. So I have a switch. And then it is also related to timing. How quickly the wiper moves. So I would have a low rate, or I would have one of the fastest rate if it's raining heavily. There could be concurrency, that we need two things to happen at the same time. Maybe there are two processors which are going to really synchronize itself and make things happen at the same time. Those would come in from Petri nets. Let's focus on finite state machines and get to it. And we'll look at a very, very simple example. We'll look at stack and how is the state behavior exhibited. So stack is, this is a stack of things. So I stack something. So I would have stacked 5, number 5, and then I stack 7. And when I pop, so this is push on the stack, and then I do a pop from the stack. So what is the state behavior here? The stack is empty, the stack is partially full, and the stack is full. That becomes my state behavior. A simple operation like pop. So there are two operations to your left. There is a single push and a pop. So I push 5 and I pop, so I get 5 popped out. But here I do 2 push and then a pop, I get 7 as the outcome. So with the first push, empty state gets to partial full. With the second push, it is still partial full but not yet maxed out. And with a pop, partial full, and it's going to move to one less item in the stack. So it becomes a stateful behavior. And how do we really model this? So this is state-based testing, and once you have modeled it, we would want to look at statefulness, statelessness, and each of these methods or functions of statefulness testing. If you only look at those methods, it may not be sufficient, because now you have to put the whole thing together and make sure that it's moving per the states. So for example, if I really look at only the push operation or only the pop operation, so if I look at these two operations over here, I'm going to change the color. If I only look at push and pop or push and pop over here, it's not going to make sense, because push and pop, when are they called, makes some sense and different sense when I'm looking at the entire behavior of the stack. So I could say stack is composed of functions like print, push, and pop. But the behavior has to be modeled in terms of a lot of things. Say for example, it can take 10 elements. Each element can be an integer. I can push items and I can pop items. Every pop operation pops one item, every push operation can push one item. So on and so forth. So a stateful component would always be a set of states and transition between the state. So if I may now draw a state transition diagram over here. So we're going to develop this, right? So I've got, this is empty. Stack is empty, partial, and now I have full. If I pop on an empty stack, what would happen? I remain over there. If I push on a full stack, nothing happens. If I push on a empty stack, it will be going to be partially full. If I keep pushing on a partial stack, I could get a push here and it may be partial, or ultimately I get a push and the stack is full. Now I do a pop and a pop and a pop. You can clearly observe that we have got three states. And which are our states? Our states are, this is one state, this is another state, and this is a third state. And we now have transition between the states. One of the things to note here is that just remember this diagram, and I would want to clear this, and now I'm going to draw a graph based on this. So I had a pop, I did a push, I did a push, I did a push to this state, then a pop, and there was also a pop. So do you see that I can actually call them as nodes 1, 2 and 3, and I would have a directed graph. If I have a starting point to this graph and an ending point to this, I will be able to now create entire transition between node 1, 2 and 3. These are nodes 1, 2 and 3, and then I would have a directed graph, each with these edges. This is one edge, this is another, this is another, this is another, this one, this one, this one, this one. And I could start off with transition using the edges. So I can transition from 1 using this edge A, and I'm in 1. I transition using edge B from state 1 to state 2. So we start looking at the entire behavior, and I bring in the transition between the states. So a simple system like stack is now got modeled as a stateful component, providing immense possibilities. In fact, I reduced it to a flow graph, a control flow graph, as well as a graph which will allow me to traverse it. One of the things that I can do is I can traverse it now. And to make that happen, make that each traversal happen, each traversal could be a test case, and each traversal will allow us to test a bunch of things. Maybe push pop function, and also within that state. So testing a push and pop while the stack is empty, testing the push and pop while the stack is full, and testing push and pop when the stack is partially full, and depending on how the stack is partially full. So if I have the number of elements is 5 and the total number of elements that it can take is 10, and minimum number that it can have is 0, of course. If I am at 5, then a push and pop operation is still going to keep it partial full. But if I am at 9, the push and pop operations are going to behave very differently. The moment I push, I'm going to get into stack full, so straight transition will happen. This behavior is something that we would see day in and day out in various systems. And modeling will help us test. So stateful component, we see stateful components all around us. Simple things like objects and classes. We would also look at control systems, embedded systems, communication systems, and I'm sure you can name many more. So here we looked at the state-based component, empty, full and partial state. We looked at 10 elements, and to make this happen, what we drew was a state transition diagram, an extended finite state machine where we also take care of event and action. If you look at it, we had only done the event part. Now we could even do the action part over here. Simplest is a state transition diagram. We will look at using this in detail in our example in the next topic. So till then, look at what we have covered, visit the textbook, look at those 2 pages which allow us to understand the issues, where the issues come from, and how the model could be built using the tools that we have. To make this happen and to look at the system, we also need something which is known as a fault model. Fault model fundamentally comes in from a perspective where it defines a small set of possibilities where fault types can occur. So here now we're going to look at fault. So we're not going to talk at modeling right now. First, let's look at the fault piece. As we look at the fault as an area and with a finite state machine or an extended finite state machine. So fault modeling with a finite state machine or extended finite state machine can have typically say 4 errors or 4 categories. There is an operations error. Operations error happens when error is generated upon transition. There is an incorrect output function. For example, a pop or a push actually generated a wrong output. Transfer error. In spite of being at last but one element, we did not transition to the final state of being full. Or if I'm popping, final state of being, or rather initial state of being empty. Or extra state error. Probably I have now designed another state in which it goes, but extra state need not be always an error. Extra state could be works for that particular scenario, but probably not required. So it's harmless if it is there. However, from an optimization perspective, probably it shouldn't exist. Missing state error. For example, we only have the empty and full, and we do not have partial state at all. Would that be a good thing? Absolutely not. It's a missing state error. Or it is a stack of only 2 elements. So when the number of elements is 0, it is empty. When the number of elements is 1, it is full. So in fact, it's a stack of only 1 element, which makes no sense. However, that could be the way in which we define it. Not in practice, but from an academic perspective. However, these 4 errors which we spoke of, these 4 categories will definitely exist. And this become part of the fault modeling, where we can look at what are the probabilities, what faults can really come in. And these are a small set of possibilities where these fault types can occur. So let's apply this quickly to a vending machine. And a first disclaimer is that this hand-drawn and scanned diagram that you have may contain errors. So I'm going to put up a star over here and make sure that you also find out the errors if you are analyzing this particular diagram. And we will do it as a part of example, but you should look at it with a pinch of salt, saying that yes, this is not the final answer. So we have a vending machine, and now we are looking at it from both perspectives. We are modeling it as well as a fault model. So we got to look at if all states, all transitions are taken care of. So coffee button is pressed, tea button is pressed, and the sugar button is pressed, and then there is a coin inserted. So the system is idle. In the idle system, you press for tea, nothing should happen. You press for sugar, nothing should happen. If you press for coffee, nothing should happen. We have designed another state which says coin is indeed inserted, because you need money before you can dispense tea or coffee with or without sugar. So there is a coin inserted. We come to coin inserted, and we move to coin inserted piece. Then we look at sugar button pressed. At any given point in time, I could just press the coin again and it returns the coin. So I should get the coin back. Now for a moment, look at this and see if this particular transitions are really making sense. Is there an error over here? Is there a state error to begin with? Have we covered all the states? Is this the right way of designing the states? You may want to pause the video here and actually go ahead and analyze this. This is a simple problem, so you should be able to analyze it without elaborate requirements. So now that you have analyzed it, if you have spent time on it, you'll be able to figure out that there are problems in this particular diagram and there could be a missing state. Is there a missing state? With idle, coin inserted and sugar button pressed, I believe we will be able to execute all the test cases or all the scenarios. Now let's see, in idle we have pressed coffee, tea and sugar, nothing's going to happen. Now we have got coin inserted, it moves to coin inserted. At coin inserted, I press coffee button pressed, so it gives me a cup of coffee and returns back to idle. Coin inserted, tea gives me a cup of tea and comes back to the idle state. After coin inserted, we look at sugar. In fact, we press one more time sugar, it just comes back to coin inserted. Oh, wrong selection. I didn't wish to have sugar, so I do a toggle on sugar. And after adding sugar, I press cup of tea. I get tea with sugar, and here I get coffee with sugar. I get the coin in return. I get a coin in return. But if I get the coin in return, what should happen? The moment I get coin in return, shouldn't I be moving to idle state? Shouldn't I be moving to idle state? Yes. So this looks like a state error. Coin would be returned, but I would be in a sugar pressed state or sugar button pressed state. So one part is the design piece. Second is the modeling piece, what we did for the vending machine. And because of this modeling, we are now able to figure out the issues in the model. And as we understand the model and the system better, we will be able to design better test cases. Needless to say, each of the transition, each of the states, movement of states would become test cases. So my logic would clearly be, I would want to cover all states, I would like to cover all transitions, those become my test cases. So covering all states and covering all transitions. These become my test cases. So I'm going to write those things again over here. So covering the states and then transitions. Here, now let's spend some time on systems of day-to-day use and how we could model them. So there are 4 systems, out of which one is very, very well understood. Lift elevator control systems, one or multiple lifts which could be available in any building. So that's what you know of. You will be able to model the system on your own. Let's look at garage door. A simple garage door which can be opened or closed at a press of a remote button. So there is a RF button, RF unit, which is available as a transceiver on the system, as well as one with which the owners of a particular house where the garage is can close or open the door. So there would be a transceiver. So transceiver typically is kept in the car so that whenever the person arrives, opens the door, gets the car in, and then can close the door all remotely without getting out of the car. Look at what the states are going to be. Garage door open, garage door close, or garage door opening or closing, partially open states. Let's look at building lighting control system. How would our building lighting control system be? If it's an apartment complex, it does have a lot of lighting control. We'll have architectural lighting. So let's kind of put together a few things that we understand around the building lighting control system. So we have architecture lights. We'll have emergency lights. We will have certain special lighting control system. Maybe these are lights within the swimming pool. All of this will have to be controlled from a central system when we have got a huge complex. Architecture lights are those lights which also may be timed depending on time of the day. Emergency lights again would be timed, as well as when there is a power loss. Special light swimming pool again would be timed. Corridor lights. Corridor lights would also be timed or may be driven based on ambient light. So you have this building complex, you've got corridor lights. Corridor lights would be specifically timed or based on ambient light. If it starts getting darker during the day because of the clouds, you're going to have these lights come up. They'll be switched on because the ambient light has gone down. Swimming pool lights, specifically during decoration. Emergency lights, especially during power loss. Power loss also timed. Late in the night, emergency lights would also include some corridor lights. Architecture lights to show the greatness or the beautifulness of the building in the night. They'll be switched on, but probably not through the night. Only during few hours when the building would be really visible because you want people to see it. Keeping that architecture light on at midnight may not really make sense. So you see the statefulness of the systems. We can start modeling such systems. Last one is an MMI interface of an instrument. Say for example, we keep using camera, a digital camera or a mobile phone. It's like a man-machine interface, a touch interface, a keypad interface. Allows us to do a lot of functions. It's all about those states. On a screen, on a mobile phone screen, you would typically see various options, a contacts application, or I'm wanting to browse. So if I'm wanting to browse, I would start my Internet Explorer or a browser, punch in a URL. So each of these becomes states for me. And this becomes a man-machine interface for us to communicate with the machine and ultimately to the state machine, which is making things happen. So these are all high-level examples. In fact, these high-level examples through the modules are discussed in detail. We in fact go and solve problems based on all of these examples. Hence, what we have discussed is a high-level piece right now, just from a modeling perspective, but we will solve these from specification-based testing perspective, as well as even system testing perspective. So that's what we had in this particular topic. Thank you.